in applications. Thermodynamic tables. For a given pure substance, table of thermodynamic properties. Tables of thermodynamic properties can be developed from experimental data in several tables of thermodynamic properties. Can be developed from experimental data in several ways. In this section, we outline the traditional procedure followed for the liquid and vapor phases of the substance and then present the more modern techniques utilized for this purpose. Let us assume that the following data for a pure substance have been obtained in the laboratory. Let us assume following data for a pure substance. Have been obtained in the laboratory. We have vapor pressure data, for example, that is saturation pressure and temperature have been measured over a wide range. T saturate and P saturate over a wide range in laboratory. Pressure specific volume and temperature data. And temperature data. In the vapor region, these data are usually obtained by determining the mass of the substance in a closed vessel and then measuring the pressure as the temperature is varied. This is done for a large number of specific volumes. A large number of specific 3. Density of the saturated liquid. And the critical pressure and temperature. zero pressure specific heat for the vapor. This may be obtained either calorimetrically or from spectroscopic data and statistical thermodynamics. Calorimetrically, spectroscopic data and statistical thermodynamics. From this data, a complete set of thermodynamic tables for the saturated liquid, saturated vapor, and superheated vapor can be calculated. Saturated liquid, saturated vapor, and superheated liquid, saturated vapor, saturated vapor, and superheated vapor. Can be calculated. The first step is to determine an equation for the vapor pressure curve that accurately fits the data. One form commonly used is given in terms of reduced pressure and temperature. LNPR C1 T0 C2 T0 1.5 T0 3 C4 T06 TR, where the dimensionless temperature variable is D0 equals to once the set of constant has been determined for the given data. The saturation pressure at any temperature can be calculated from this equation. The next step is to determine an equation of state for the vapor region that accurately represents the PVT data. It would be desirable to have an equation that is explicit in V in order to use P and T as the independent variables in calculated enthalpy and entropy change from the previous equations, respectively. However, equations explicit in P as a function of T and V proved to be more accurate and are consequently the form used in the calculation. Therefore, at any chosen P and T, the equation is solved by iteration for V so that the T and V can then be used as the independent variable in the subsequent calculation. The procedure followed in determining enthalpy and entropy is best explained with the aid of this picture. The procedure to determining enthalpy and consider this picture. Let the enthalpy and entropy of saturated liquid at state 1 be set to 0. In state 1, enthalpy and entropy at 1 set to 0. The enthalpy and entropy of saturated vapor at stage 2 can then be calculated from Clapeyron equation. Stage 2 can be calculated. Change phase. Clapeyron equation. Which was SFG on VFG. The Clapeyron equation say that the dP sat on the temperature, or another relation dP sat on dt h minus h h prime, for example, on t v 0.1 v prime. This case 1 and 2. The left-hand side of this equation is found by differentiating the equation before LNPR Vg is calculated from the equation of state using Pg Vg at Pg from the equation before, and Vf is found from the experimental data for the saturated vapor. Vf from experimental data. From state 2, we proceed along this isotherm into the superheated vapor region. The specific volume at P3 is found by iteration from the equation of state. The internal energy and entropy are calculated from the related relation, which are DUT T 1 P on rho T V constant minus P dVt and ds can be calculated from this relation. And the enthalpy is then calculated from its definition. The properties at point 4 in the picture point 4, for example, a superheated point, found in exactly the same manner. Pressure P4 is sufficiently low that the real superheated vapor behaves essentially as an ideal gas, for example 1 kilopascal at point 4. P4 sufficiently low. Thus we use these constant pressure lines to make all temperature change for our calculation, as for example 2.5. Since the specific heat Cp0 is known as a function of temperature, the enthalpy and entropy at point 5 are found by integrating the related equations. The properties at point 6 and 7 are found from those at point 5 in the same manner as those at point 3 and 4 were found from point 2. Finally, the enthalpy and entropy for saturated liquid at point 8 are found from the properties at point 7 by applying the Clapeyron equation. Their values for pressure, temperature, specific value, enthalpy, entropy, and internal energy of saturated liquid, saturated vapor, and superheated vapor can be tabulated for entire region for which experimental data were obtained. The modern approach to developing thermodynamic tables utilizing the Helmholtz function, defined by equation 1412, rewriting the two partial derivation for A in the equation A1, the Helmholtz equation U minus Ts. Rewriting the two partial derivation, we can find P equals to rho 2 We now express the Helmholtz function in terms of the ideal gas contribution plus the residual contribution A star plus AR or dividing by RT alpha star, delta and alpha r, delta and t. In terms of reduced variable, we have these relations. Delta rho on rho RC TC on temperature, critical point. To get an expression for the ideal gas portion alpha star, we use the relation A star H star RT T star S, in which H star is TS star, H star on DT. S star equals to the S star 0 plus R Ln rho T on rho 0 T 0, where rho 0 equals to P0 on RT0, P0 T0 H star 0 and S star 0 constant. In this relation, the ideal gas specific heat Cp0 must be expressed as an empirical function of temperature. Cp0, a function of empirical function of temperature. This is commonly of the form of equation in Appendix A6, often with additional terms. Some of the form of the molecular vibrational contributions as shown in Appendix 6. Following selection of the expression for Cp0, the set of equations gives the desired expression for alpha Z star. The value can now be calculated at any given temperature relative to arbitrarily selected constant. It is then necessary to give an expression for the residual alpha R. This is commonly of the form Mk plus Nk exponential Lk, in which the exponent ik and lk are usually positive integer, while jk is usually positive but not an integer depending on the substance and the accuracy of fit. Each of the two summations may have 4 to 20 terms. The form of this equation is suggested by the term of Lee-Kessler equations. We are now able to express the equation of states as this relation for an arbitrary gas in experimental setup it can be delta one plus delta alpha r since we have these relations. On rho P on rho RT and delta differentiating the previous equations in the previous page and substituting to this relation result the equation of states as the function of z, a function of delta and tau, the non-dimensional noise of temperature and the another quantity which was density. In terms of empirical coefficient and exponential of the equations alpha r. These coefficients are now fitted to the available experimental data. Once this has been completed, the thermodynamic properties S, U, H, A, and G can be calculated. S, U, H, A, and G. Calculated directly using the calculated value of alpha star at the given t and alpha r. From the previous equations, we can obtain this relation for various properties. S on R and P constant at rho minus R RT on alpha on U on RT S on R A on RT on delta. The next relation for H on RT URT plus Z calculated before, and G from RT, A on RT plus Z alpha plus Z. This last equation is particularly important since at saturation the Gibbs function of the liquid and vapor must be equal. HFG TSFG. Therefore, at the given temperature, the saturation pressure is the value for which the Gibbs function calculated from for the vapor V is equal to the calculated for the liquid V. The starting values for this iterative process are the pressure from an equation of the form before with the liquid density from given experimental data as discussed earlier in this section. This method for using an equation of states to calculate the properties of both the vapor and liquid phases has the distinct advantage in accuracy of representation in that no mathematical integration are required in the process.